factor theorem. So factor theorem states that if we let p of x be a polynomial, if c is a zero of p, that is, p of c is equal to 0, then x minus c is a factor of p of x. Conversely, if x minus c is a factor of p of x, then c is a zero of p. So factor theorem basically tells us that if the remainder is equal to 0 after dividing a polynomial by a certain linear polynomial such as x minus c, then the x minus c is a factor of the polynomial p of x. And let us have this example. Determine if x minus 3 is a factor of this polynomial. So we can actually have two solutions here. One by using the synthetic division. The other one is by using the concept of remainder theorem. Because we only need to know what is the remainder after dividing such polynomial by this divisor. So let us have the solution using the synthetic division first. So here we have a divisor of x minus 3. So equating this to 0 and applying APE. We have to add 3 to both sides of the equal sign. So we have this bx equals 3. So this will be our coefficient in our synthetic division setup. While looking at our polynomial, so here we have the exponents of 4, 3, 2, but there is a missing term, such as the term containing the x having the exponent of 1. So writing the coefficients first of x raised to 4, followed by the coefficient of x cubed, which happens to be negative 1, and we have the negative 18. So this time, since that the x is missing, we should have the coefficient be 0. And finally, our constant term, we have a negative 7. And let us start with our synthetic division. So bring this down here and multiply 2 with 3, we have 6. Adding these two numbers together, we have a 5. And we simply have to repeat the process. So 5 times 3, we have a 15. Adding this together, we have a negative 3. And multiplying this, we have a negative 9. And adding these numbers together, we have a negative 9. And multiplying this gives us negative 27. So notice that the remainder here is not equal to 0. Instead, this is equal to negative 34. Since the remainder is not equal to 0, therefore, x minus 3 is not a factor of this polynomial. And let us have another example. So here we have to determine if x plus 2 is a factor of this polynomial. So having x plus 2 be equated to 0 and applying APE, we have to add negative 2 to both sides of the equal sign, having this equation. So this is a 0, so your x is equal to negative 2. So our coefficient set up would now have a constant of negative 2. And for the polynomial, notice that we have 4, 3, 2. So again, the exponent of 1 is missing. So let us write the coefficients immediately. So we have a 2 followed by negative 1, negative 18. So since the term containing the x having the exponent of 1 is missing, we have to write a 0 for such, and now we have the 32. So let us have our synthetic division. So let us bring this 2 down here and multiplying the numbers together, we have a negative 4. Adding this, we have a sum of negative 5. And multiplying these two numbers together, we have a positive 10. And again, adding this, we have a negative 8. And multiplying these numbers, we have 16. And adding this together, we have a 16. And finally, multiplying these two numbers together, we have a negative 32, and this gives us a remainder of 0. So since that the remainder is equal to 0, therefore, x plus 2 is said to be a factor of such polynomial. And now for our next example, here we have to show that x minus 2 is a factor of this polynomial. So again, we may apply synthetic division for this, but since I have already used the synthetic division to answer the first problem, then let us use the remainder theorem for this. So since this will be the divisor, we have to identify first the value of the c by having this be equated to 0, so that we must be able to have this be rewritten as x equals c. Doing so, we have to apply the APE by adding a positive 2 to both sides of the equal sign, giving us the value of x be equal to positive 2. So remember that for us to get the remainder of dividing such polynomial p of x by this divisor, we have to change all the x's with such value of c. So let me write first the original polynomial here. So having the value of c be equal to 2, so we must have our polynomial be in terms of p of 2 by changing all the x's with such value of 2. Doing so, we have our x here be equal to 2, so having the cube of such value. So here we have 7. Again, we have an x, so we need to change this with a positive 2. So the same for this x. And now we only need to simplify the resulting expression here. And we have the value of 2 cubed be equal to 8. While here we have to evaluate this first. 2 squared gives us 4, and multiplying this value to 7, it gives us a positive 28. So next we have this be equal to 4, and we have to subtract a 40. So let us have this. It is equal to 36 plus 4, which happens to be 40 minus 40. It gives us a remainder of 0. So since that the remainder is equal to 0, therefore, this x minus 2 is said to be a factor of such polynomial p of x. And now let us have another example. So here we have to find the value of k, so that the polynomial x minus 2 is a factor of 2x cubed minus kx minus 3. So in this problem, our goal is to find the value of k, given the condition that this is a factor of such polynomial. So it applies that the remainder after dividing such polynomial by x minus 2 is equal to 0. So that means if we identify the value of c by restating x minus 2 to x equals c, so we must have this be equated to 0 first. and applying the addition property of equality. So adding a positive 2 to both sides, it gives us x equals 2. So since that the remainder theorem tells us that we only need to change all the x's in the given polynomial p of x with a2 for us to have the value of the remainder, then let us change first all the x's in the given polynomial p of x here. So your x would now be a positive 2. So again, the x right here becomes a positive 2. And since that it was stated that this is a factor of such polynomial, therefore, I have already told you that the remainder is 0. So we have to automatically set this particular statement pertaining to the remainder be equal to 0. So therefore, you will notice that the equation only contains a single variable, and we can easily have such value by manipulating this equation. Doing so, we have to evaluate 2 cubed here, which happens to have a value of 8, and multiplying the 8 with 2, it gives us a positive 16. So since that we have to multiply here the negative k with the positive 2, so it gives us negative 2k. So writing this, negative 3. And now we have to combine the similar terms here, and we have 16 minus 3, which happens to be 13. And writing the negative 2k, for us to find the value of k, we must manipulate this equation by having the 13 be transferred to the other side of the equal sign. So applying the APE, so we must add the opposite of positive 13, which is negative 13, to both sides of the equal sign. So doing so, so let me have the resulting equation be written here. So 0 plus negative 13 is negative 13, while this gives us a 0. So writing only the negative 2k. So for us to have the value of the k, we must eliminate the negative 2. And the division property of equality tells us to divide both sides of this equal sign by a negative 2. So it becomes a positive 1, and 1 times k is equal to k. And here we have the value of k be equal to negative 13 divided by negative 2, which is 13 over 2. So this will be the value of k, so that the x minus 2 is a factor of this polynomial.